Online we can hear.
Yes.
Can you?
Okay, yeah, now we can hear you.
Oh, you can hear me online. Okay,
Yeah,
now
thank you.
everyone here.
All right, so yeah, you have 15 minutes and 5 minutes for questions.
Thank you.
Thank you. Would you please share your screen? Yeah.
Yeah. Do you see it properly?
Yes.
So yeah, so thank you for the opportunity. I would allow to be in the room and discuss with all you people, but I'm happy for the opportunity to present like this remotely. So I'm Henrik, and the work that I will present here today I did in the Institute for Solar Physics in Stockholm University, and then I'm just in a transition period. So in the future, for future references, you will I'm in the European Space Agency. And yeah, I will just jump straight into it. We have seen some other really nice works on radio data this week. So practically here, I will just mention this, that I then have been specializing in using solar observations at millimeter wavelengths. And why we want to do this, it's practically because we want to be able to measure the chromospheric temperatures very accurately, which then is which is very neat with this type of wavelengths. But the neural network imaging technique that I will present today, it's not limited to this type of wavelengths. It could essentially be used for any type of wavelengths. And then to observe these at millimeter wavelengths, we use the Atacama large millimeter and sub-millimeter array, the ALMA. And that is then consists of this interferometric array of these antennas to achieve then a reasonable resolution at sub-arc second resolution. And the antenna configurations, they come in this, what we see here in the middle of this screen, from the more compact one to the more extended one, which then sorry, I can't see my own everything on my screen here, which then results in these resolutions that we see here on the right hand side. So this is then the observables at 3 millimeter from a numerical model of the solar atmosphere. And up here to the left, we see the observables in the original resolution of this model. And then following is the different antenna configurations from the more compact one, the C1, to the one of the more extended one, the C7. But for the solar observations, we are limited from, because of technical difficulties, we are limited so far to somewhere around here, the C3. So this resolution is what we have to deal with so far. The data that exists so far is this resolution that we see here. And okay, sorry, I forgot there was a lot of clicking on this line. So then one of my projects that I've been working with, it is that I've been looking in this numerical model and look for these small scale brightening events that is then appear like this in the temporal evolution of these brightness temperatures as these peaks that we see here on the left hand side of the plot. In the solid line, then it is the original resolution of the model. And then of the resolution, observational resolution that we have in the ALMA observations, then it is what the line that we see here that were marked here with these arrows. And then if we look at for many of these peaks in the data, then and plot them at original resolution compared versus the observational resolution, then we get this distribution plot that we see here in the middle, which then is somewhat linear, so one can then extract some sort of correction factors that in principle could be used then in observational data. But we see here they have very large uncertainties. But nonetheless, in the observational data that we see here on the right hand side of the screen, in the red circle here, it's a small part of the sun. Then in this data, this is snapshot of the temporal evolution of the data. In this data, then we find all these brightening events that we see here from these colored plots. This is the temporal spatial coordinates of these plots. So the brightening excess temperature of these events then result in this distribution that we see down here. And if we then use these correction factors that we get from the numerical model, then we can shift this distribution of the brightening events towards the solid line that we see down here. But then with, as we see, significant uncertainties. And that then sparked this is the main reason then for the neural network approach that I will be presenting here. And that is because some of the events are well resolved and some are not, but there is no way to tell just from looking at a snapshot like that. So then this neural network that I trained, it's based then on a convolutional neural network and then combined with the recurrent neural network. And this is then combined with the long short-term memory cells. So in this, so it has this architecture that we see here on the right-hand side. And these cells then has 2D convolutional operations that then is good to distinguish the features in the time series of these 2D images. And then practically what I do is to train this network. It is that I have two different numerical models. The first one that we have seen here before in the previous slides. That is, it's a Bifrost model, and it is a longer, quite significant long model, and it has a large span of parameter space in terms of magnetic field strength and topology, and then the contrasts of the dynamic small-scale features for these purposes. And then we have what we see here down here is the validation data set that is a very short one that we ran just for this purpose to validate this neural network. And it features then the quiet sun. And so on the left here, we see in the regional resolution, and then in the middle of the degraded resolutions, we degrade it to what corresponds to other observations. And here on the right, we see the difference then between these two. For each of the simulations. And what is worth to see here is that we have plus minus, I don't know, 3000 Kelvin at scales that are similar to the resolution element, to the PSF. So that is what then creates problematics when we want to study these small scale features. So in the training, then I basically then feed to the neural network a time series of the images of the observational resolution, and then I ask it to estimate these correction factors, that is the difference between the degraded and the original resolution. And then the results looks something like this. Here we have the observables at one snapshot, and the corresponding then the difference between the degraded and the original resolution. In this upper left plot, in the middle here, upper middle plot. And then here to the upper right, we see the estimations of the neural network that then should be as similar as possible, let's say, to this other plot. But we see that it's much more smooth in the small scale features, which is expected, and as there are limitations in the observational resolution, how small features that the neural network would be able to pick up. But then this map of correction factors, that is the output result here, then it's very useful because it can be used then to create these masks of accuracy across the field of view. Here is an example of 70% accuracy and 90% accuracy, which then is useful if one wants to choose specific points in an observational data set for in-depth analysis. And then to come back to these brightening events that I was studying, then we see here on the left side an example from the validation data set. of one of these brightening events at observational resolution in the dashed line here, and then the solid line in the high resolution. And we see here the neural network in the dashed dotted line. They give a really smooth estimation of the brightening event in the temporal domain. And then looking for many of these type of brightening events, then we create a similar plot as we had before with a high resolution versus the observational resolution in a validation data set. And we get this type of distribution that we see here in the middle. But then letting the neural network estimate these brightening events, then we get these plotted to see here on the right-hand side. And there I just wanted to then point towards that if I look at the accuracy that this corresponds to, then it corresponds to more or less what would be achieved with error configuration C7. It was the more extended one in the first plot, in the first slide that we saw. So it's quite significant improvement. And then if we then, so here is a snapshot of the validation data set again, at the regional resolution, the high resolution, and the observational degraded resolution. And here to the right, we have then, if we take the observational resolution and we apply the map of correction factors to this one, then we get what we see here on the right hand side. And it's obviously a lot of improved contrasts. And also we see here that, for instance, these small scale, very bright points, they are well resolved. The neural network managed to bring them out quite nicely compared to what we see in observational resolution, and also what you would get if you apply a regular 2D deconvolver in the map of the observational resolution. So that was the, let's say, the main results. And then there are some side results that I find worth to mention here also. It is that we can estimate other things with the neural network also. And one of the examples is the radiation formation heights. And the height of the formation of the millimeter wavelengths, millimeter wavelength radiation, it varies very much than with these small scale features of the chromosphere. As we see here, it's on the order of 1 megameter. This is to another wavelength, as you know, because it can be an order of 2-3 megameter, and we see it in the next slide. Here we have a plot then of the intensities as a comparison. And then if we plot then the similar plot again, but instead the brightness temperatures towards the versus the formation heights, then we see we get this fairly linear distribution again, which then points towards this is what the fairly linear but with large uncertainties, but this is what the neural network achieved well previously on the brightness temperatures. And here is just an example of this. If I feed it the time series of the intensity maps at observational resolution and ask it to estimate the formation heights, I get these results that you see on the far right-hand side here. And here in the other plots are comparisons then directly from the numerical model. So this then is very useful to get a hint of, if you look at a specific small event, to get a hint of if this is actually formed very high up or further down, which then helps the analysis of these events. Yeah, this will appear in some conference proceedings. It still is in press. And this is what I mentioned here, that there is significant differences between, you can have these events, they can appear at more or less 1 megameter or 3 megameter height in the atmosphere, and this is then very important to take into account.
You have 3 minutes left.
Okay. So basically, this is the last plot here. What I wanted to mention here also is that it could be valuable to estimate the opacities of these different wavelengths, and it comes from this, that you have these different components at significant different heights in the atmosphere that then all contribute to the observed intensities. And also we can note here that we have significantly different bands that we see here that are different wavelengths in the millimeter wavelength region. And but this is more ongoing work that I have this idea that I can estimate the opacities of the millimeter wavelengths with the neural network also. So, okay. So then I leave you here with the conclusions that I have in the shape of this image that you saw before, because I think it concludes very well what this neural network then can do for the millimeter wavelengths observations. And with that, I'm happy to take questions, or if you have it later, please just contact me.
All right, thank you very much. Do we have questions? Yes.
That was great, thank you. Am I right in thinking that, so these are simulated interferometric images? Do you do the machine learning on the image itself, or do you do it in visibility space and then create the images as if you were doing interferometric imaging, if that makes sense?
Yeah, that makes perfect sense. It's a great question, because I didn't want to go in on that, but if you would read this, the PDF, the paper that is linked in the PDF here, you will see that I didn't want to go in on that here, because there are some other technical details that comes in with the observational data that I discuss, but it becomes too much to discuss and try to sell well in a short presentation. But here, what I've showed you here, I focus on just the observables as a perfect antenna, if you would have a super huge antenna. But it just has to do with the precisely what you mentioned, that you get these, you don't measure at all the wavelengths, right, in an interferometer, but that is not, it turns out also that it's not so necessary to do that here. The neural network managed to distinguish that quite well.
Okay, cool, thanks. I'll definitely have to check it out.
All right, any more questions? We have one more. If not, then thank you very much.
Thank you.